Okay, so the last couple of examples that I want to look at for 10.3 are similar to what we did converting between polar and rectangular, or polar and Cartesian, but instead of converting single points from one coordinate system to the other, I want to convert equations. This is something we do a lot in some of those later classes that I had mentioned. And the idea with these first three cases here, these I'm going to call Cartesian equations because the variables are x and y. It'll be in polar form if I can change all of the variables to some combination of r's and thetas. Now, oftentimes, if you can, we usually want to think of r as a function of theta. Normally, when we talk about functions in Cartesian coordinates, we usually think of y as a function of x. It doesn't always have to be that way, but that's typically what we're looking at. So in these cases, I'm going to attempt to isolate the r. It's not always necessary, but oftentimes that's what we're looking at. So let's start with a. A is actually very straightforward. I have x squared plus y squared equals 16. But x squared plus y squared is equal to r squared. That was one of our conversion formulas. So I can say that r squared is equal to 16. Now at this point I can take square roots of both sides of this to get r equals 4. One thing I want to point out is that the equation r equals 4, normally when you take square roots of both sides, you would pick up a plus or minus right here. It's actually unnecessary in this case. And the reason for that has to do with what this represents graphically. If I were to graph this, this represents the set of all points that are 4 units away from the origin. That would be, or the pole, rather. That would be a circle centered at the pole with a radius of 4. If I had made this r equals -4, well, we would still think of that as the set of all points that are 4 units away from the pole, but we would interpret that negative in the context of what to do with that angle theta for any one of these points in polar coordinates. For example, if I had a point here at 5 pi over 4, let's say that was the angle, I can interpret that as -4 with an angle of pi over 4. If pi over 4 is over here and r is negative, that tells me to swing that around and come back here. But the point is that all of these points are still on the exact same circle, so it doesn't do anything more for us to include that plus or minus there. We'll talk more about the graphs in the next section. Let's go on to B. I'm going to do this over here. So B, I can start by plugging in some conversion stuff, some conversion formulas right away if I wanted to. But what I'm going to do instead is expand this out before turning things into r's and thetas. So for this one, if I expanded x minus 1 squared, that's x squared minus 2x plus 1, and then I have this plus y squared equals 1. Okay, now I'm going to cancel the 1's from both sides, and that's going to leave me with x squared plus y squared minus 2x equals 0. I moved the x squared and the y squared next to each other only because I know that together these things are equal to r squared. So that makes it a little more clear what to convert. Our x squared plus y squared can become an r squared minus 2x. So remember x is r cosine of theta. Okay? That's equal to r cosine of theta. And again, if you remember, the goal is to represent this as a function of r if possible. So if I were to factor an r out of this, r times r minus 2 cosine of theta equals 0. From my zero product property, I know that technically leads me to 2 equations, either r equals 0 or r minus 2 cosine of theta equals 0. Now, as we said before, for any point in polar coordinates, if r is equal to 0, regardless of what the angle is, that's always describing the exact same point. It's the pole, or the origin, if you want to think of that in rectangular terms. This equation, if we think of it graphically, it has a point, at the origin. In other words, if I plug in the correct value for theta here, I can get this r to come out to 0. And I could see that by adding 2 cosine to both sides and then attempting to set r equal to 0 and solve that for theta. But the point of that discussion is that this r equals 0 here is redundant because this equation essentially includes this one. So what that means is we don't need that. It's not because there's anything wrong with it, it's just redundant. And so this equation gives us the entire description of the set of points that this equation up here did, and it's sufficient to just work with this. I'm going to add the 2 cosine of theta over, giving me r equals 2 cosine of theta. And that's going to be how I represent my answer. Notice again, r is isolated so that r is being thought of as a function of theta. All right, let's try C next. So for C, we're starting with y equals 2/3 x minus 1. Okay, for this one, I'm gonna start right away just by substituting in those conversion formulas. Y is equal to r sine of theta. This is equal to 2/3 r cosine of theta minus 1. Okay. Now this next step is technically unnecessary, but I'm going to do it anyways. Sometimes it's nice to not deal with fractions, so I can eliminate this fraction by multiplying both sides of this by 3. 3r sine of theta equals 2r cosine of theta minus 1. Oh, sorry, that would actually be minus 3 now, wouldn't it? Because I multiplied by 3. Again, I could technically just leave it this way. Everything is in terms of r's and thetas, but we want to be solving for r. So I'm going to subtract this term over here so that it looks like 3r sine of theta minus 2r cosine of theta equals -3. Then I'm going to factor in r out so that it looks like r times 3 sine of theta minus 2 cosine of theta equals -3. And then I can solve this just by dividing both sides by the stuff in parentheses. So I get r equals -3 over 3 sine of theta minus 2 cosine of theta. Now what's interesting about this is it sort of illustrates what equations of familiar graphs look like when we convert to polar coordinates. Again, if I go to this case up here, the graph of this circle was given in rectangular coordinates as x squared plus y squared equals 16. Not the most complicated thing, but it's not a very super straightforward equation. In polar coordinates, this circle just looks like a constant function. R equals a constant. That's about as simple as a function can get. So polar coordinates are very, very good at describing things like circles, things that are circular or have something close to a circular sort of shape. We'll investigate the graphs of polar functions in more depth in the next section. Things that are very far from circles, things like straight lines, are better described in rectangular coordinates. Notice y equals 2/3 x minus 1. That's the equation of a line. In polar coordinates, it has a somewhat complicated looking equation that defines it. But that's because polar coordinates are not quite as good at describing things like lines. Okay, let's try this the other direction. This will be the last thing that we do in this section. So here we want to rewrite the following equations in Cartesian form. So turning r's and thetas into x's and y's using those conversion formulas. Let's start with A. So if r equals 9, this is another constant function. If we go back to this example here, when r was equal to a constant, I was expecting to see a circle, right? And remember, this is what circles look like in Cartesian coordinates, circle centered at the origin. So what I'm going to do is start by squaring both sides of this so that it says r squared equals 81. I'm doing that because I have a conversion formula that uses r squared. r squared is the same thing as x squared plus y squared. And so now we have the Cartesian form for that equation. Circle center of the origin with a radius of 9. That's pretty straightforward, that one. Let's take a look at B. R is equal to 5 cosecant of theta. So we don't have any conversion formulas that use cosecant in any way. However, if I were to rewrite this, I know cosecant is the reciprocal of sine, so I could write this as r equals 5 over sine of theta. That works fine. Then if I were to multiply both sides of this equation by sine of theta, that's going to give me r sine of theta equals 5. Okay? Well, I recognize r sine of theta as just y. From my conversion formulas, that's equal to y. So this is the equation in Cartesian form of what I was given in the first place, r equals 5 cosecant of theta. Again, this describes a line. That's a horizontal line passing through 5 on the y-axis. In polar coordinates, those involve things like secants or cosecants. If this were a secant, I'd actually see that this is the graph of a vertical line. But again, we're not looking at graphs quite yet. We're going to be more focused on that in 10.4. Let's go to C. I'm going to do this right here. C has a complicated looking expression, but it looks similar to what we got for C in the previous example after converting from rectangular to polar. So I'm expecting something kind of similar. I'm expecting this to look like the equation of a line. Okay, so let's start with r equals 10 over sine of theta minus 4 cosine of theta. I'm going to multiply both sides by this denominator. R sine of theta minus 4 cosine of theta equals 10. Then let's distribute the r in. So this becomes r sine of theta minus 4r cosine of theta equals 10. Finally, notice that the r sine of theta here and the r cosine of theta here are going to turn into a y and an x respectively. So this becomes y minus 4x equals 10. Or if we want to put that in slope-intercept form, y equals 4x plus 10. I actually could have left it in this form. That's the standard form for the equation of a line. Nothing wrong with leaving it in that form right there, but that's what we were expecting to see, a line. Okay, so that's going to be it for 10.3.